Hello everyone, I'm Seono.
I'm 준석전.
Our project is real-time web conferencing service for individuals with speech disorders. Since the COVID-19 pandemic, online web conferencing platforms such as Zoom or Google Meet have become a necessary platform of everyday communication. However, these platforms are mainly designed for people who can speak clearly, and they provide limited accessibility for individuals with speech impairment. Because most platforms provide a basic speech-to-text caption feature, but these models are trained on data from people with clear pronunciation. Therefore, when recognizing speech from users with speech disorder, they often show a very high word error rate. As a result, these recognition limitations reduce the equality of participation. To solve this problem, we propose a service called GOOM. GOOM is a customized web conferencing service that supports both verbal users with unclear pronunciation and non-verbal users who cannot speak. Through this system, our goal is to enable equal participation for all users, regardless of their speech ability. This diagram is our service overview of meeting feature. When a user creates a new meeting or joins an existing one, they first need to select their user type. Because speech impairments can occur in many forms, depending on the severity of muscular or neurological damage. Some people may speak with reduced clarity, while others may be unable to produce speech at all. Therefore, our service classifies users into three types. First, general users. Second, verbal users with speech disorders who produce unclear or inconsistent speech. And third, non-verbal users who cannot produce sound at all. The system processes different input data depending on the user type. Next, I will explain how we implemented the GOOM service. This diagram shows our system architecture. Our service provides three recognition paths based on user type. First, general users are processed through Google Cloud Speech API, which recognizes clear speech with high accuracy and reliability. Second, verbal users with speech disorders are processed through fine-tuned Whisper Tiny model, and it is deployed on NVIDIA Triton Inference Server. Finally, non-verbal users are processed through an auto AVSR lip reading model, recognizing speech only from lip movements. We also implemented speech activity detection on the front end to recognize when users start and stop speaking. This prevents unnecessary AI processing and reduces latency. For audio, we used the Web Audio API to detect voice and silence automatically. For video, we used MediaPipe to track lip movements and trigger lip reading only when lip movement is detected. Finally, for real-time video conferencing, we used WebRTC integrated with the Stream Video SDK to support smooth multi-user communication. For caption delivery, we used WebSocket to broadcast text output from the STT or lip reading models in real time. As a result, each participant received synchronized captions.
This is our implemented service UI. The main home screen allows user to start a new meeting or join with a code. When creating a meeting, users can select whether they have a speech impairment and choose their communication method such as speaking or using only lip movements. In the meeting screen, video conferencing is supported with automatic captions generated through speech or reading recognition. User can also use the chat panel on the right for text communication. And this is our experiment and result. The first experiment focuses on visual-only speech recognition or lip reading. Our system is based on the auto AVSR model, which predicts spoken words without using any audio, relying solely on visual information. When a video is input, we first use media pipe to detect and crop the lip region from each frame. These lip ROI sequences are then processed through those networks, allowing the model to run the temporal movement patterns and generate text prediction. The model was trained and evaluated on the LRS3 dataset and achieved a 19.1% WER under silent video conditions. This demonstrates that the system can provide meaningful recognition performance for nonverbal users in real meeting environments. The second experiment focuses on users who can speak but produce unclear or inconsistent speech. For this group, we developed a customized speech recognition system by fine-tuning Whisper model on the Torgo desultory speech dataset. We evaluated performance by comparing Whisper Base and Whisper Tiny in terms of WER and inference speed. Our results show that the Onyx optimized Whisper Tiny model provides approximately 2.8 times faster inference than Whisper Base. Although it has a slightly higher WER, the significantly lower latency makes it more suitable for real-time captioning for desultory speech. So in conclusion, our service integrates audio and visual recognition to provide accurate, low latency, and real-time captions for all users. It removes communication barriers for people with speech disorders, enabling equal participation and fostering a more inclusive digital environment. In future, we plan to develop personalized models and add multilingual and translation features to broaden global accessibility. From now on, I will show you our demonstration video.
First, a general user creates a meeting and copies the meeting code. Then the user sends the code to the opponent. The opponent joins the meeting as a non-verbal user who can only use lip movement. As you can see, her microphone is turned off. But thanks to our lip reading recognition, captions appear automatically like this.
I'm fine. Also, communication is good.
Since the other participant is a general user, Google STT accurately recognizes his speech. Here is another example of lip reading.
Okay, I have one small update. I will send the file today.
For speech recognition, we compared Google STT with our fine-tuned STT model. On the left window, the user creates a meeting as a general user. On the right window, the user creates a meeting indicating that she has a speech impairment and can produce unclear speech. Because we cannot recruit real speech impaired patients, we tested with a sample speech disorder dataset. The label was all the big baseball players get traded.
All the big baseball players get traded.
The accuracy difference was significant. While the right window, our fine-tuned STT, predicts the text correctly, Google STT produced an incorrect transcription. Here is another example as well. The label was, "He will allow a rare lie."
He will allow a real lie.
The left output, real life, while our model produced correct answer as real lie.